Edgar.
Great. Thanks, Rob, and thanks to Ned and Alex as well for putting together a great program. I'll primarily be talking about these two papers here. And one of the nice things about this program is I don't have to have a long set of introductory slides to make sure everyone is on the same page, because I'm pretty sure most people know about many of the developments. The very quick summary is that last year, there was a lot of work about deriving the page curve for Hawking radiation in black hole spacetime. And you could roughly think about it as, derived from sort of two perspectives. First, there are these fantastic papers, which in some sense used holography to derive the page curve. And then there are these papers later in the year, which took the perspective of the Euclidean gravity path integral. Now, as Daniel talked about in his talk, for those that were there, these approaches in some deep sense may actually be the same sort of approach if you believe the conjecture that Euclidean gravity gives correct answers in holographic systems. But in any event, what I want to talk about today is sort of taking the Euclidean gravity perspective that we've used in very many different spacetimes, cosmological spacetimes, etc. So maybe we can think about more general spacetimes than AdS spacetimes, which is what these papers were focused on. And this will sort of be a two-part talk. The first half of the talk will be thinking about flat spacetimes in 2D. And the second part of the talk will be thinking about more general spacetimes, and in particular cosmological spacetimes in higher dimensions like 4D. And then again, if you sort of believe Euclidean gravity has something to do with holography, you can start thinking, what does this tell you about a potential holographic description of these systems? Okay, that's the quick overview of what I want to talk about, and I'll jump very quickly into the flat space model that we looked at in the paper with Tom and Andy. So the model is a 2D dilaton gravity model. It's a CGHS or RST model. I'm going to take this opportunity just to sort of introduce this model to people who maybe are not familiar with it, because it's quite an interesting model. So it has two names because they're roughly speaking two different models. The difference in them is entirely this term here. So if you include this term, it's called the RST model. If you don't, it's called the CGHS model. And we'll see in a second why this term is there, what role it's playing. So here's a classical action. Okay, it looks a little bit messier than we're used to, but some dilaton gravity action, and it has a CFT action that's minimally coupled to the metric, and as usual, not directly coupled to the dilaton. Okay, that's important for the solvability of these models, similar to JT. Then there's a conformal anomaly term, which integrated up into the action looks like this. And this is altogether, think of as the quantum effective action, which is exact at large C. And in fact, it's equivalent to the flat space JT action. Well, what's sometimes called the flat space JT action. The flat space JT action is the thing that's written here. So there's some set of field redefinitions that take you from these fields to these fields. This dilaton is a capital phi. It's not the same as this dilaton here. And the CFT action sort of comes along for the ride. It's still minimally coupled to the metric in this frame, and again, not coupled to this dilaton. And if you are in conformal gauge, meaning this gauge, which is almost always a good idea in 1+1 dimensions, then there you can sort of understand the connection of these, or part of the connection of these two actions through this U1 current. So this full action with the RST term has a U1 current given by this. This is conserved. And it's equivalent to the shift symmetry in this dilaton phi. And that's why Russo, Susskind, and Thorlacius, RS&T, added this term. It was so that they could have this U1 current. The CGHS action without this term has a U1 symmetry in the classical action, but it's broken by the anomaly. RS&T added this term so that once you include the anomaly, the U1 current is still preserved. And therefore, altogether with the anomaly term, the RST action can be field redefined into, again, what's sometimes called the flat space JT action. Okay, so that's one perspective on this term, and it leads to nice analytic features of the model. Okay, so if you do some field redefinition and gauge fix further, you can reduce the RST equations to a very simple set of equations. They're the ones written here. This field omega is some nonlinear combination of the dilaton phi. You could actually think about it as being closely related to this field capital phi here, okay? But the equations of motion are very simple. They look like this. T flat is just a stress tensor without taking into account the contribution from the Weil anomaly. This will become clear in a second. And this model is often analyzed in a particular way. The dilaton is restricted to some range. This 1/4 is convention dependent. It's not important, but it's restricted to some range. And this is in contrast with some analyses of, let's say, JT and AdS2, where the dilaton is integrated over the entire axis. Here we want to restrict it to some range, so we have a sort of understanding what the black hole solutions look like in the model. And as usual in the dilaton gravity models, they're inspired by dimensional reductions of higher dimensional models. So cutting off this dilaton is to be thought of as cutting off space-time where the transverse sphere shrinks to 0 size, because the size of the transverse sphere is related to the dilaton in 2D. Okay. So let's look at some solutions of this model. So one simple solution you can write down is called the linear dilaton vacuum. There it is. It looks like this. This, of course, does not look linear. It's called the linear dilaton vacuum because if you'd written the solution in terms of the original dilaton, lowercase phi, it would have been linear. But in any event, in terms of this field omega, it looks like this. If you write it in terms of the metric variables, the metric looks something like this. It's just flat, okay? And the stress tensor is given in this way. So as I said, T flat is a stress tensor ignoring the contribution from the Weil anomaly. There's a contribution from the Weil anomaly. And these relations tell you, you can probably check in real time against these formulas that the stress tensor in X coordinates, which cover, let's say, the entire 2D Minkowski space, or the stress tensor in the sigma coordinates, which cover the right Rinther wedge, are 0. That's one reason why we call it the vacuum. So you put the matter in the vacuum, solve for the metric, you get flat space. And there's this cutoff that I mentioned before. We want to cut the dilaton off at omega equals 1/4. So we cut off space-time here. This may look a little surprising for people who haven't seen it before. It looks like it might be some sort of naked time-like singularity, but the interpretation of this cutoff was taken to be in many of the previous works, like the origin of polar coordinates in higher dimensions. So again, if you think about a higher dimensional model, the transverse sphere sort of shrinks to 0 size at the origin of polar coordinates. That's not a singular point, of course. And if you think about an S wave coming in, some imaginary S wave coming in toward the origin, it's just going to kind of reflect out and go back out. So in quantizing the model on this background, what people often imposed here was reflecting boundary conditions along this omega equals 1/4 line. Okay. So this model is not impressive because it can produce a solution to the vacuum. Almost any model can do that. It's impressive because it can produce a solution for an evaporating black hole. It has some strange features, this evaporating black hole, which I won't get into. People can ask me at the end or on the Slack page. I'm going to ignore those weird features. They all kind of happen near the evaporation endpoint. But in any event, the solution is very, very simple. Here's the linear dilaton vacuum part of the solution. And then there's just some step function, which corresponds to some delta function shockwave that you send in. So the Penrose diagram looks like the usual ones we draw in higher dimensions. You send in a shockwave, you create a black hole, it evaporates, and then you have the Minkowski space left at the end. In a non-Penrose diagram like what we had before, it looks like this. Here's the omega equals 1/4 line. So we're in vacuum before the shockwave, which we just put at x plus equals 1. The shockwave comes in, and once it hits this omega equals 1/4 line, it actually turns it around and makes it space-like. And this is interpreted in all the previous works and in our work as being like the black hole singularity. So it remains space-like for a while until the evaporation endpoint where it turns around and becomes time-like again. Okay, and the stress tensor is given by this for the solution. And what's incredible about this model is that you could compute the sort of stress tensor at Scri plus exactly in this model. So the metric is flat in these sigma coordinates. There's some sigma tilde here. The tilde is just because it's a shifted coordinate compared to the usual one. So there's usual exponential map between the sigma and the x coordinates. But for sigma tilde, there's some shift. It's not important. The only important thing is we want to measure the radiation as seen by an asymptotically inertial observer. So since the metric is flat in these coordinates, we want to measure the stress tensor in the sigma tilde coordinates. And we find this very simple function. And it's, you can analyze it pretty immediately. So sigma tilde minus starts from minus infinity, which is I naught, and then it increases all the way, it increases as you go up scribe plus. So if you plug in sigma tilde minus equals minus infinity here, you see that the stress tensor is 0. So there's no Hawking radiation whatsoever. And as you scale it up, you see that the stress tensor very quickly approaches a roughly constant value of 1/4. So this shows you analytically through this very simple solution, the Hawking radiation for a black hole made from collapse. Okay, so it's one of the reasons why people really liked this model. Okay, so you have that solution and you can go and compute what the entropy of the radiation is in this model. And that's what was done by these authors in an incredible paper. I would recommend people reading it. There's a lot kind of going on in that paper. And what they found is that the entropy of radiation basically follows the Hawking curve. It's given by this function. So sigma tilde increases, it becomes roughly linear in sigma tilde minus. There's some UV and IR divergent junk, which we could ignore, but basically the entropy increases without bound. And the conclusion that they reached in this paper, and is reached by other people analyzing similar situations, is that this model has remnants. Okay, and this is, you should think about this very much in the spirit of Daniel's talk. If you were there, this theory was thought of in the framework of canonical quantization. And canonical quantization, the quantum gravity entropy of radiation is just the semi-classical, it's the same as the quantum field theory on a fixed background entropy. And that's just the Hawking answer. And that's just the right answer in the theory defined in this way. Okay, so that's all just a quick review of this model. Now, what we did in this paper is to think about what role something like replica wormholes or islands or what have you would play in this situation. And I already said this, this model is defined sort of on a fixed topology is in the framework of canonical quantization. So there are no replica wormholes as traditionally defined. The proposed modification is to sum the theory over topologies. Now, once you do this, it's not clear what the UV completion is. It probably needs more details. It's very unlikely to be UV complete on its own. Well, it's not UV complete on its own. But if you do sum over topologies, then you expect to get the island rule, which says that the entropy of radiation in the theory of quantum gravity is given by this exterminization problem, where the generalized entropy as usual has a gravitational contribution and a QFT contribution. Okay. If I have time, I'll talk about a sort of replica analysis we did in the paper as well, but I may end up just skipping over it. But this is the formula we have. And to apply it, we need to make a further assumption, which is that we're going to treat scribe plus as non-dynamical. So when we measure the entropy of radiation at scribe plus, it's basically going to play the same role that the bath played in the computations of AdS2 gravity glued to a flat space bath. Okay, this is an important assumption. If you did not treat it as a non-dynamical place where you could define a region whose entropy you're computing, then the analysis would change completely. Okay, now we can revisit the evaporating black hole, and there was a similar analysis done by these two sets of authors as well. Okay, I'm not really going to go into the details because the punchline is that there are no surprises. I put here the particular approximations being made, consider a sort of massive black hole, consider times that are of order of the mass. And then if you apply the island formula, you find that you have this minimization. Here's the UV and IR junk that I referred to before that one can just ignore. And you find that at a certain time, this minimization leads to an exchange of saddles, and you go from having no island in the interior of the black hole to having an island in the interior of the black hole. Okay, the page time is given by this fraction here, which is a third of the evaporation time. And that is just because black hole evaporation is non-adiabatic or not isentropic. Entropy is produced in the semi-classical picture. So the curve looks something like this. And again, this is not really a surprise. It's fully in line with what was expected from the analysis of Pennington or Omhary, Engelhardt, Rolf, and Maxfield. Any quick questions about the CJHS or RST analysis?
I don't see any questions.
Great. Okay, so that's the answer we get there. So maybe I'll just go through this kind of quickly just to give people an idea. So we also did a sort of like replica analysis in the paper, which applies to a sort of general theory of dilaton gravity. This CFT is again minimally coupled to the metric and not coupled to the dilaton. And we did basically a local analysis. So assuming that there was, assuming you wanted to put dynamical defects in the gravitational region, we analyzed the equations of motion in that situation. So expand the 2 degrees of freedom, the dilaton and the conformal mode of the metric, expand the stress tensor, use the conformal word identity to see how the stress tensor is related to the entropy, which is the thing that you want to compute. And if you assume replica symmetry and expand the equations of motion in this limit, near the defect and for n near 1, then if you solve the constraint equations, you actually find the extremization piece of the island formula. So this just pops out of the equations that you want to extremize this combination. So this, it's not a complete analysis. We didn't solve actually for the replica wormholes and show that they dominated. We just did a local analysis and found that these extremization equations come out in some general dilaton gravity. So that lends some support. And I think it's interesting to think about this question because, naively, you might get a little bit confused about replica wormholes in the flat space case, because replica wormholes are, topologically non-trivial configurations. We're very used to thinking about topologically non-trivial configurations for hyperbolic manifolds. But for flat manifolds, it's not clear that it's not clear that you should have such configurations. And an important aspect of seeing that such configurations make sense is what I said at the beginning of this section, that we treat scri plus non-dynamically. What that means at the level of equations of motion is that you don't solve the gravitational equations of motion for the twist operator that's inserted at scri plus. So those equations of motion remain unsolved. You think about it as field theory on a fixed background. It's singular at that point. There's no back reaction that smoothens it out. And taking that into consideration, you can sort of see that you can satisfy Gauss-Bonnet or whatever other topological constraints, and you can have these non-trivial manifolds for otherwise an exactly flat background. And remember, in the flat space JT frame, the background is exactly R equals 0. Okay. That is all I'm going to say about the flat case. And I'm going to change gears and talk about sort of looking for islands more generally. And this is going to be content from this paper with Tom Hartman and Yukun Jiang. And we're motivated by the question is, how do we search for islands in general dimensions and spacetimes? And part of why we're motivated, at least maybe why I was motivated, is I spent a fair amount of time searching for islands and trying various things of, what if I put the region of radiation I'm computing over here? And what if I put it over here? Will I find an island? And is sort of doing some educated guesswork. But it would be nice if there was a way to write down some conditions that didn't depend on the region R whose entropy you're trying to compute, just to see if some spacetime can host an island at all, okay? So I'll make that clear in a second. And there's some necessary conditions you could write down. There's one necessary condition which actually first appeared in this this paper that I already referred to, and it just comes from the extremization condition. Okay, the extremization condition says that you want to extremize the generalized entropy on I union R. Lambda plus is just an outgoing null derivative, so this is just one of the extremizations that has to be true. You can rewrite this equation pretty simply. Add the QFT entropy on I and subtract it. Okay, that didn't do anything. And then also subtract the QFT entropy on R. This dd lambda plus is the null outgoing derivative of the endpoint of the island. So if it acts on S QFT of R, it just annihilates it because this derivative acts on the island endpoint. And these two terms are just the generalized entropy expanded out. I'm sorry, these two terms are the generalized entropy. The area A over 4 and the S QFT on I union R is just this generalized entropy expanded. Okay, so this just rewrites the extremization condition. But now notice that I've grouped them into two terms that might look familiar. This is just the generalized entropy of region I. In particular, it no longer refers to region R. And that was the motivation. I want to somehow get rid of the dependence on region R and just have something that only depends on region I. And this is the mutual information, or minus the mutual information between I and R. Okay, so in particular, I can rewrite this again in this way. It's the equality of these two quantities. But now this quantity, we have a nice inequality for. Okay, this derivative is greater than 0 because its outgoing null derivative is increasing the size of I. So under increasing the size of one of the terms under mutual information, you find that this has to be positive. And the inequality is flipped for an inward null derivative. Okay, you can repeat the step. You find for an inward null derivative, this is shrinking the size of region I, so this has to be negative. Altogether, it says that the boundary of I has to be in what's sometimes called the quantum normal region. Those are just, okay, well, that just means this. Quantum normal region is defined in analogy to classically normal regions where, you know, outgoing things go out and ingoing things go in, but you replace the area that appears in the definition of classical normality with the generalized entropy. So you replace with the area plus the matter entropy. So you find these inequalities. Okay, and notice these are necessary conditions that have to be satisfied if you want an island region I for any radiation region R. And this is in a general number of dimensions. Okay, so that's one set of necessary conditions you can write down. Another set comes from the minimization condition. Okay, the minimization condition says not only do you need to extremize to find an island, then you need to compare the island entropy to the non-island entropy. So in particular, if you want the island to dominate, then you need the generalized entropy, this combination, to be less than the ordinary QFT entropy on R. Okay. We can again rewrite this. You have added the, added and subtracted the QFT entropy on I, and then rearranged some terms to write it this way. And okay, somewhat naively, and I won't go into the more careful analysis, you can use the Araki-Lieb inequality on the right-hand side to show that this is greater than 0. And then you can push this term to the right-hand side to get this inequality. Okay, now why did I say naively? And in addition to saying naively, snuck in this hat and this squiggle. It's because these combinations are not UV finite. So this is not a generalized entropy, which is expected to be a UV finite combination. This is SQFTI minus A over 4. And a similar statement goes for this right-hand side. So there are various UV divergences. And to make this statement precise, you need to regulate these divergences. You need to put in a cutoff and get contributions to the entropy that scale with the cutoff and then compare them to the existing terms. And okay, the details of this are in the paper. But if you do that, what you find is sort of the, I think the moral thing that everyone already understood, which, okay, this S hat means the finite part of the entropy on I. And the squiggle means that we've sort of ignored terms that are subleading compared to this A over 4. So it's not an exact inequality. There are subleading terms here. And what it's saying is you need to have a lot of entropy in I, right? If you don't have a lot of entropy in I, then you're never going to, have the entanglement with any region R be sufficient to include the island. Because remember, this was coming from the minimization condition. So that's all it's telling you, that you want a lot of entropy in I. And that's it. I think that's intuitive. I think many people already thought about islands this way. And a fun sort of phenomenological sidebar, phenomenology in quotes, is that you can sort of check this condition in our universe. And in our past light cone, if you assume that you have a thermal matter entropy, then this bound is violated actually at the electroweak scale, which I don't know, sort of funny. We didn't really know what to make of it. It does not mean, and we'll see in a second why that is, we don't think it means that there's an island at this time, which is something like 10 to the minus 14 seconds or something like that. We don't think it implies an island, basically because in the situation, the other necessary condition won't be satisfied. But anyway, this is just a fun sidebar. It's not going to appear again. There's a third necessary condition, which we talked about in our paper, which is actually probably the most constraining one, but I'm not really going to get into that. I'm just going to focus on these two to make the point. And the point is that they are necessary conditions that have to be obeyed by an island. So in particular, the boundary must be in the intersection of these two regions. And they're actually very constraining. That's sort of the point of our paper. You can use this to rule out the existence of islands. They're not sufficient as far as we know. So we don't know that you can use them to rule in islands, but we'll see some examples where they do seem to be sufficient. So let's look at some cases. I'll just flash some pictures now. So here is, for example, radiation dominated FRW spacetime. You start off with some singular Big Bang, and it's not accelerating. So it's any non-accelerating FRW Penrose diagram will look like this. There are no future horizons. And if you plot the two regions, the quantum normal region, meaning the region that satisfies this, is given by this diamond here, or this triangle here. And we call this the sort of Bekenstein violating region, because it in some sense looks like a Bekenstein bound. It's comparing the entropy to the area. And that region is down here. And notice they have no overlap. Okay, their overlap is actually near the singularity. So it can't really be trusted. So this spacetime does not seem like it can host islands. Okay, this is a four-dimensional calculation where the entropy being considered is sort of spherical regions around the origin. Okay, when you compute generalized entropys, you need to fix to some sort of a spatial region that you're computing the matter entropy for. Okay, so that's one example where it doesn't seem like you can have islands. A very closely related example is, ignoring what happens in the past, if you have some matter plus a positive cosmological constant, so you end up being cosmological constant dominated, so a future de Sitter spacetime, then again, you can draw the two regions, the quantum normal region and the Bekenstein violating region, and you again see that they will not have an overlap. Okay, so these are some negative cases where you can use these necessary conditions to sort of rule out the existence of islands. And again, this does not reference some region R. Okay, all it references is some island region I. And again, we consider, for example, spherical regions, and you can rule out islands in that case. Okay, those are some negative cases. So maybe let's go to some positive cases. Let me see how much time I have. Okay, I think I'm doing good on time. So one example is where there seems to be some non-trivial overlap is a crunching cosmology. So here you have a Big Bang. Let's say you have matter plus a negative cosmological constant. This is what the Penrose diagram will look like. You'll end in a crunch. And now you'll have a non-trivial overlap between the quantum normal region and the Bekenstein violating region. And it's some sliver way out here. Okay, as I said, these are necessary conditions. So it's not clear that you can necessarily have an island that exists with its endpoint in this region. But one of the things we did is compute in a particular example and show that you can actually have this spacetime host an island. I won't go into the details of the example, but basically what you do is you start off with the thermal field double state on flat spacetime. Okay, and on one of the two sides of the thermal field double, you turn on a scale factor, which is the scale factor that leads to a Big Bang and a big crunch, and you turn on gravity. Okay, so this spacetime does not have gravity. This spacetime has gravity, so you could compute. You can define regions here without worrying about subtleties. And for the entropy of some region R over here, as long as it's sufficiently large enough, it'll have an island in the crunching cosmology. Okay. So that's a sort of positive case where the sliver actually does suggest that you can have islands, and you can actually, by doing some more work, define a setup where you can see what the region is that has the island endpoint in this green region. So that's one example, and again, this is a four-dimensional example. And another reason these conditions are useful is, to compute islands, you often need, unless you have some nice factorization, which happens in the black hole case, you need two region entanglement entropies. And entanglement entropies in higher dimensions are already difficult, let alone two region entanglement entropies. And these conditions at least reduce you to single region entanglement entropies. So you can, in some cases, at least rule out the existence of islands without necessarily being able to compute two region entanglement entropies. In this case, we could compute them because there's some nice formulas in the case of a thermal field double, but more generally, it's difficult. Okay, let's consider another example. We'll go back down to 2 dimensions and consider JT gravity in 2-dimensional de Sitter space. 2-dimensional de Sitter space's Penrose diagram is this rectangle. It can be unwrapped, but I won't consider the unwrapped case. It's this rectangle here. And if you consider, again, sort of symmetric intervals around this point, so this line and this line are identified in this Penrose diagram. There's symmetric regions around this point. Here are what these conditions tell you. The overlap region is some small sliver that lives way out here. Now, if you look closely in this Penrose diagram, there are squiggles over here. And the reason is that one of the solutions for JT gravity in DS2 exactly parallels the dimensional reduction of Nariai black holes in higher dimensions. These are like Schwarzschild de Sitter black holes in the extremal limit. So the Schwarzschild de Sitter Penrose diagram, I mean, it extends past this, but it has a de Sitter inflating region and then a singular region due to the Schwarzschild black hole. And the JT gravity in DS2 solutions share that feature. So the dilaton goes to -infinity up here and down here. That's why there are these squiggles, because it's singular. And it goes to +infinity up here and down here. So this is thought of as the inflating region. So this computation done here is very much like a black hole in AdS or flat space. It's just now the asymptotics or the space-time it lives in is not AdS or flat space, it's de Sitter space. But the physics is very similar. In particular, you can find an island, again, whose endpoint lives in this little green sliver in the overlap region. And that island is the island for the entropy on this slice here. And the interpretation of this is exactly like the computations of an evaporating black hole in AdS or flat space. That you just measure the entropy in the exterior of the black hole, and if you measure enough of it, then an island will appear in the interior of the black hole. Okay, the physics is precisely the same. One of the last things I wanted to say is this example is actually kind of closely related to the crunching cosmology example. So, people often say the interior of black holes is like a crunching cosmology. The reason for that is, well, A, it's singular as the approach to singularity. B, if you sort of expanded the metric near there, it looks, well, it is really some anisotropic cosmology. So one of the pictures that one might try to build toward, again, using this here, is a picture that looks roughly like this. So I'll explain what this is. So the concrete calculation that's done here is we again have JT gravity in 2-dimensional de Sitter space. That's this entire space-time up to this orange dashed line here. And what we have in here is flat space JT gravity. So we glue JT gravity in 2-dimensional de Sitter space to flat space JT gravity in this diamond. We glue it across this orange cut. And if you compute, again, the entropy of radiation in this region R over here, you'll find an island that lives, again, in the black hole interior over here. This setup is very much like this setup here. It doesn't really matter whether the region you put it over here or put it inside a flat space bubble here. The point is it's still measuring sort of the entropy of radiation. But drawn this way, what this picture is supposed to be inspiring in one's mind is a picture of potentially something like eternal inflation. So in eternal inflation, we believe that there are these stable supersymmetric flat bubbles that appear. So this orange dashed line where we glued 2D de Sitter space to 2D flat space is supposed to represent a Coleman-de-Luce bubble nucleation of a stable supersymmetric bubble. And this black hole singularity in this region here is supposed to represent a crunching bubble, which is supposed to be, unless you end up in a stable end state like the supersymmetric zero cosmological constant bubble, it's believed that you'll end up crunching. So these crunches dominate a lot of future infinity. And the picture we're sort of trying to build toward is that an observer that lives in this flat bubble maybe has access to physics outside of his or her cosmological horizon. And this can maybe implement some form of cosmological complementarity, whatever that means. Now, this picture, I should admit now after saying all that, is a bit of a fake. So the state that's considered on this entire spacetime is the Hartle-Hawking state, which has particular features with respect to the radiation that's measured by this observer over here. To actually do this computation for a realistic bubble nucleation into a stable bubble, you would need the details of a Coleman-de-Luce bubble nucleation and an understanding of what the entropy in that spacetime looked like. And that's very hard. It does not, as far as I know, look like this situation here, but I don't know very much about what the entropy in that situation would look like. So I think it's an interesting thing to try to understand. As it stands, this picture is just a souped up version, as I said before, of the black hole island type calculations. Okay, let me summarize and then I will stop. So these 2D dilettante gravity models, CGHS and RST, they sort of hide information. If you canonically quantize them, they have remnants. The entropy of the radiation increases without bound. So something you might want to do is modify these models with a sum over topology. And this seems to lead to a unitary page curve. Again, it's a important question to understand once you do this, how to UV complete the model. Okay, that's not understood. The other point is that these consistency conditions, I talked about two of them in this talk. They can guide the search for islands in higher dimensions, and we use them to rule out certain cosmological islands. And we use them to rule in and then actually check and construct islands, at least in the case of a crunching cosmology, where the matter was taken to be in a thermal state. And something one might want to do is think a little bit more carefully in these more general situations. If you believe that, whenever Euclidean gravity is telling you correct things, that it has something to do with holography, maybe one can use the various understanding of islands and other things that come from Euclidean gravity to understand what a holographic picture for these sorts of spacetimes can look like. All right, that's all I wanted to say. I'll stop there.
Okay, thank you, Edgar. That was a very nice talk. We have lots of time for questions if people want to raise their hands. But I'm going to start in your general constraints. You said you had 3 constraints, but sort of glossed over the third one. Can you say a few words what that last constraint is?
Sure. So roughly speaking here, we had a condition that was the derivative of the generalized entropy with respect to I, and it gave it a lower bound. The third constraint can be thought of as sort of giving an upper bound to the generalized entropy. And it's what you do is, once you have this island region I, you can apply these quantum information arguments that we're doing to this region I. But you could also consider something like its complement. It's a region that we called it region G in the paper, but you could sort of apply these various inequalities to the complement. It's a little bit more slippery to handle that third condition, because in this setup, it's perfectly reasonable to consider the complement of region I, it's just the rest of the space-time. But in something like a black hole space-time or something like that, where region R and I are in the same space-time, you need to figure out what to pick as this region that's sort of connected to I, but is not really connected to R. And part of making that condition as constraining as possible requires picking that region outside of region I in a clever way. So in this example, for example, the crunching cosmology one, if I just considered that third condition, it would be a little sort of teardrop region right around here. So it sort of seems more constraining than both of these. So it's actually a very useful condition. It's just, if you were only to choose one condition to check, that would be the one to use. But these two are sort of sufficient in all the examples we looked at least to pick a nice region for you to sort of focus your attention on.
Okay. Next, Alex, can you unmute yourself?
Yeah, thanks. Thanks for the nice talk, Edgar. A quick question at the very beginning, like first or second slide, you said that the quantum effective action is exact at large C. I was just wondering what happens at finite C and how would it change everything else you said after that?
That's a good question. So one of the things about this model, which is related to the difficulty in this cutoff on the dilaton, is it's not really understood how to define this model with this cutoff at finite C. So this has been analyzed in, large C with this one loop correction. Exactly, but it's not clear that if you put the cutoff on the dilaton, that it comes from some theory that exists at finite C. So I think this was an open question that was left in the 90s, and I don't think there's been much progress on it. You can, of course, sort of choose to not put this cutoff on the dilaton and then just quantize it without the cutoff. And then it'll, I think, start looking more like the JT and AdS2 story done through, well, either Euclidean or Lorentzian quantization. But with the cutoff, it's not known what the finite C physics looks like, or if it exists.
I see. Thanks.
Mm-hmm.
Are there any other questions? People raise their hand. No, I'm not seeing any questions. Oh, Juan, do you want to unmute yourself? Can you unmute yourself?
Yeah, so you assume that the cosmological spacetime or the entropy we have in the cosmological spacetime comes from entanglement to another system, right?
Yeah.
Now, if we start from something like inflation, we wouldn't expect that, right? We would expect that we essentially start from a pure state, and maybe things are entangled within our universe, but not with some other universe.
Right.
So that also is something that seems to make islands more difficult in the I mean, for some application to our universe.
Yeah. I think what you're saying is, even when I was considering this case, I was considering the best case scenario, which is that the state is actually mixed in this entire single universe.
Right.
Yeah. Even with that generous assumption, it didn't seem like you can get an island.
Yeah, that's just a comment.
Yeah. No, I totally agree.
Okay. Takiro, can you unmute yourself?
Hi, Edgar. So, what is the boundary condition for matter fields at the cutoff omega equal 1 both part?
The usual choice made there is that you pick reflecting boundary conditions. So in the end, a lot of the computations that are done for the entanglement entropy are like VCFT type computations because of that boundary condition.
I see. I see.
And again, the motivation was because of this, the analogy to the sphere in higher dimensions. Now, of course, with these 2D dilettante gravity models, there's always a competition. How many of the features of the higher dimensional model do you keep? To what degree do you ignore that and say this is a well-defined model in 2D, I'm gonna quantize it directly? But the thing that was often done and was done in our paper is that you put reflecting boundary conditions, and it's because the interpretation is like it's the origin of polar coordinates.
I see. I see. And another question is, what is in this slide? So, what is the implication of this condition in AdS case? Which regions are excluded?
These two conditions?
Yeah.
So for the AdS black hole case, it would actually look very much like this. So this is, a black hole in de Sitter, but the black hole in AdS would also look something like this, that the island region kind of needs to be, well, very large, and endpoint has to live out here. And that's what we see in the evaporating black hole situations for black holes in AdS.
I see. Thank you.
Yeah.
Maybe I'll ask another question. You mentioned in the first part of your talk the idea that you have now flat manifolds, but you seem, well, with the island rule, you seem to be hinting that there are replica wormholes. I just wondered if you had more comments on that.
Not well. I can say some thought process I had, which was in some sense incorrect. But another reason to try and think about the replica wormhole perspective is, okay, one potentially incorrect way to think about the problem is, as I said, CGHS and RST maps to flat space JT, and okay, there are various sets of authors, some set of, I think, Russian authors who've been trying to understand that connection. Where am I going here? But you see now, if you think about this model in this way, this flat space JT model can be thought of as a dimensional reduction of flat space gravity in 3 dimensions, in the same way that JT and AdS2 can be thought of as a dimensional reduction of AdS3 gravity. Okay, then you might say, well, AdS3 gravity has black holes, and that's why it has islands, and that's why JT and AdS2 has islands. But flat space gravity in 3D doesn't have black holes. So why should this theory have, so this theory doesn't have black holes, so why should it have islands? So that was another perspective in thinking islands sort of shouldn't exist here. And if you apply the island formula and interpret it in a particular way, it'll sort of always give you islands. So one wants to try and check it in some way, either from the Euclidean gravity perspective or something like that. So that was another sort of motivation to do the replica analysis to some degree and see if such solutions are allowed or not. And okay, like I said, we didn't do the global analysis, we just did a local analysis, but in that analysis, at the least you sort of popped out the externization condition. So it seemed reasonable that you can have islands coming from these non-trivial saddles. And again, they're allowed because, well, there are boundaries and there are these singular points at infinity. So there isn't actually a constraint to having these topologically non-trivial configurations.
Okay.
And well, I'm not sure what Subrat is talking about this conference, but he may talk about the perspective where you treat Scri plus dynamically instead of non-dynamically. And if you do that, then the conclusions can potentially change. From the island perspective, one way to think about it, I think, is now you sort of need to extremize the endpoint of the region on Scri plus. And of course, if you do that, it's just going to want to run across the entire space-time and give you 0 entropy. And that's just kind of a time-independent answer. And I think that's one way you could think about the island formula, that's sort of being consistent with, I guess, the constant entropy that Subrat may speak about.
Yeah. Okay. Thanks.
Sure.
Are there any other questions? I don't see anybody raising their hand. So maybe we can thank Edgar again for his very interesting talk. Thank you, Edgar.
Thanks.
It seems that we have time now. We'll take a 10-minute break